Okay, fair enough. Um,
Okay, so
all
what we'll
right.
do is we'll just go through the presentation first, and then at the end we'll give people opportunity to ask questions. So it usually works better to do it over the typing part. So at the end we'll have questions typing through the message panel to everyone on that. If that's okay.
Yeah, that sounds fine.
Okay, do you want to go ahead then? Thank you.
Yeah, yeah, and thanks for inviting me, Matthew. Effectively, this sort of came out of we were just having a discussion about the sort of epidemic models that sort of at the very foundation of infectious disease. And it turned out that there's a pretty strong overlap with some of the stuff being done in, I guess you could say, basic chemistry. So we thought we'd just I'll just give an overview of some of the links and try where possible to link it into current COVID-19 research, though I imagine you might be a bit tired hearing about that. Um, so yeah, so and as silly as this graphic is, it's kind of like just trying to it does underpin the overall idea, which is that we are describing epidemics by mixing infectious people, for these guys with the thermometers here, with susceptible people who are those that can be infected and who might just be going along their merry way unaware. So I guess to sort of just get us on the same page is there's a bit of a description about what an epidemic model is. So it's a way of putting down in math how infectious disease or say the number of infected in a population might change with time. So it's inherently about dynamics and hence kinetics. And why we need models is sometimes from the biology we might have some degree of understanding or knowledge about how we think a pathogen or disease might spread, but to get that sort of pinned down a bit rigorously, we tend to sort of put them into these computational boxes that sort of describe the interactions between various components of the epidemic. And so that allows us then to just sort of generate testable hypotheses and then see which ones pan out. And sort of some of the chemistry is that there's a lot of data to inform this. And while we can't really do experiments, we will use surveillance and field data to sort of guide and try and project forward what those certain hypotheses lead to in terms of maybe deaths or say the level of ICU beds required. So sort of like project ahead of time. And that's sort of the main um, sort of benefit of models is just allowing us to sort of quantify and to also make as clear as possible the assumptions behind our predictions so we could assess potential risks, costs coming onto the future. Obviously, as you go further, as you project further and further onto the future, there's more uncertainty, and sometimes models also help to quantify that uncertainty. And real-time usage, as in now with the coronavirus, it's being used a lot to inform public health intervention choices, the biggest of which currently is to sort of design exit strategies for post-lockdown. So just to sort of provide an idea of some of the historical usages or misusages of epidemic models and ideas. We have a bit about the plague in a little village near Sheffield, where I mean general knowledge would have said that quarantine is a good idea. The rector of that community convinced the members of that village to quarantine themselves against the spread. And what actually happened, because it may not have been as clear at that time of the impact or exactly the dynamics of the impact of being in close contact with rats and fleas, it led to a higher mortality rate than was in London. And this was maybe an example where some more precise modeling could have been beneficial. On the other end, you have Ronald Ross, who's famous for describing the malaria and the link with the parasites involved. And he was also one of the early developers of epidemic models in terms of, say, what we think of them now, which is these mathematical or computational objects. And what he did is he developed a sort of model that showed that if you force the mosquito population below some threshold, you actually prevent some future outbreaks of malaria. And that was at the time a little bit unexpected, because people didn't believe that you could really stop it by reducing the population, and it saved a lot of people. And for his analysis of the malaria life cycle and so on, he won a Nobel Prize. That's not the end of that story, because it doesn't always work to do this, because you could have immunity being lost to malaria. But that's just going on. It was one of the first instances of some really good epidemic modeling. So why then do we even need to really try and link this up to chemical kinetics? Well, fundamentally, with infectious disease epidemiology, what we're interested in is the behavior of populations of individuals, populations of infected individuals in this case. And you could sort of think of them as somewhat similar to concentrations of molecules or numbers of molecules in some fixed media. As mentioned before, we can't do experiments, at least most of the time, but surveillance data is what we'll use to try and understand, you could say, the kinetics ongoing. Often in these models, you start off by assuming homogeneous interactions, which means which is very similar to chemistry, where you have like a big beaker and everyone sort of randomly collides around and reactions occur at some rate. And sort of the main tie-in is the fact that some of the most famous and popular and only used models being used even now in infectious disease epidemiology tend to be linked to the principle of mass action. That is often the key dynamic underlying these models. So that in itself makes a very clear link to chemistry. Other points with noting is that the equilibria of those regions which describe the epidemic are important. You might want to know if you end up in a disease-free state, or if you have something that is seasonally endemic. Some of the ways that we talk about how the epidemic is progressing are quite similar. In chemistry, you'll talk a lot about half-lives. In epidemiology, they often talk about doubling times, which is sort of the converse of that. That's very much related to this exponential dynamic. And the other key point is, because we're thinking about this in terms of reactions, in terms of spread, when we want to control an epidemic, it often comes down to changing rate constants, as will become clearer in the next couple slides. So there is a significant overlap, both in what they want to achieve and how they achieve it between at least undergraduate chemistry and some of the early basic fundamental epidemiology. So probably the most popular and widespread model in infectious disease is what they call compartmental model. And you might have heard of people talking about this a bit on the news. It has its origin in some foundational work by Kermack and McKendrick, and there's some contributions by Ross of malaria fame. And this model, all it effectively says is we're going to separate a population into a number of different species, or they say compartments. So we have susceptible people who, as I mentioned before, some group that can be infected, so they don't have immunity. Infected people who have been infected, and then we have recovered people who've gone through the infection and come out. In some models, recovery could also code for deaths. And what we then do is we sort of take these three compartments or beakers and we mix them together, look at their interactions, which are often stoichiometric, and that describes the epidemic. To see that a bit more clearly, so we look at our SIR. Oh yeah, and I should probably mention this compartmental model specifically is called the SIR and is the most popular. Now the SIR mixes all the species together, and you could have the key reaction is this contact process in which you have a susceptible person reacting with an infected person, and it leads to two infected people. So that's the transmission process. And the rate constant of that K is linear in both S and I, and K depends on what we call beta and N. So beta is sort of like a contact rate. So it describes how many people you come into contact with per unit time example. And N is the total population size, which can be thought of all the molecules within a specific media. And this also, we also see that the susceptible susceptibles get used up in this reaction. So we could also look at it in terms of the depletion of the susceptibles, which is sort of like the key reagent being used up. And this equation alone is actually sort of the main process for spread. There's also another important second reaction in which people are infected after some time with rate constant gamma, they become recovered. And this is a first order rate reaction, depends on the concentration of I, depends on gamma. And gamma has a special role as well. It's sort of, or at least one of a gamma is sort of seen as the mean infectious period. So the length of time over which someone who is infected can transmit. So effectively, we have two important reactions and two important rate constants. And a key assumption usually made, at least initially in these models, particularly SR, is that we have a closed system, meaning that we don't account for births and deaths into the population, which is usually fine for epidemics that don't last, say, of the order of years. If they do, then you do have to account for those changes. And going forward, I might not always refer to the square brackets notation because sometimes it's easier to talk in terms of absolute numbers. But I hope it will be clear that, particularly with this equation, that the key players in the epidemic have a very chemical analog. So let's look at those reactions and see what they suggest. So if we simulate a population with 1,000 individuals, we could sort of run those reactions and see how the epidemic behaves. So as mentioned before, the susceptibles get depleted or used up until some equilibrium point. Some infected people become recovered. There's sort of an interplay also with the susceptibles. And this bit is sort of the infected rising somewhat exponentially. They reach a peak, which we've been hearing a lot about, the peak of the epidemic. And then they sort of die off due to a lack of, say, substrate to continue to react with, because we have a fixed population. Now, this curve is what they call the epidemic curve. You've probably heard a lot about it. And while this simulation is deterministic, often we do stochastic ones. So we have a bunch of various curves describing the epidemic. What I haven't shown here is that because it's stochastic, the epidemic often early on can die off on its own. So there'll actually be a bunch of epidemics that just never took off. Now, in terms of describing what's going on, what's going to be important are the equilibria and, of course, the rates of growth, all of which depend on the rate constants. And our main goal in infectious disease epidemiology, especially when you have emerging pathogens or emerging diseases such as COVID-19, is to try and infer some of these dynamics given some surveillance data. So one of the key things we might want to infer is the basic reproduction number. Now this number has been spoken about a lot, as it's effectively the key analytic for contagiousness. And you could sort of think of it as a dimensionless rate constant combination. Its definition relates to the average number of secondary cases per primary case, usually defined at the beginning of the epidemic, strictly, because there's an assumption there that everyone is susceptible. So early on, if we look back at our reactions, when S is about N, so we're saying that everyone is susceptible and we introduce one infected person, the reactions could be approximated by the simpler form, which is in the stochastic chemical we'll call the linear birth-death process. And if you look at the dynamics of this, you could actually pull out that R naught is simply the ratio of the rate constants. Note that the N, which was in the previous formulation, that got cancelled out by this bit of the approximation. Now, so this number here is sort of one of the key, you could say, prognostics of how the epidemic will go. And you could sort of think about it in two ways. You could think about it in terms of this birth-death way, in which every generation we initiate beta infections and then gamma infections die off, so they go to recovered. Or you could also think about it as a product of an infection rate, which is the beta, as I said, describes, for example, your contacts with susceptibles. and the duration of infectiousness, which is the lifetime of I, the 1 over gamma term before. So beta times 1 over gamma. Now, as we look at this number practically, we have a bunch of diseases here, and as you can see, R0 can vary quite a lot. Measles is known to have a particularly high contagiousness, if you want to call it that. And COVID-19 has one of about 2.5, so you can see that about here. And I guess one of the key things to know is that while R0 does tell a lot about epidemic, as will become clear soon, it's a bit of a complicated factor to interpret because it depends on a number of different things and also is affected by a number of different things, which is why we can enact control. So it might depend on how people behave, the biology of the infection, for example, airborne. For measles, one of the reasons it has a very high rate of spread is that it is the particles they're very light and can persist and travel long distances in the air. Could be environmental factors, and you could sort of think of this in chemistry as just having reactants with different forms, or in biology as having repressors or activators that could, within some complex set of unknown reactions, lead to changes in R0. So R0 is a simplification, but it's a very important one. So let's go back to R0 and think about, as I mentioned, why it's so important. Now, if we apply something like the isolation method in chemistry, where we have other reagents in excess, we could again get this sort of scenario with the birth-death process. Solve that birth-death process, where we've removed the other dynamics, we can actually explicitly derive this exponential growth. And this, as you know, has been part of a big public health policy about talking about trying to reduce the factors in this. Key in that is the exponent R0 and the infectiousness duration, which is 1 over gamma. So this exponential growth pops out, and when we look at the exponent, you see the interesting thing that if R0 is greater than 1, we will get growth, but if it's less than 1, we could see the epidemic dying off. While this equation is strictly, or I guess technically, only true early on, there are analogs later on in time. So the idea of this threshold is actually very general. So this just brings us to sort of the crux of the social COVID response: flatten the curve. So these curves here, they're all they're sort of the epidemic curves I showed you, for example, when I showed the stochastic ones a few slides back, like these, particularly that. And they track the number of infections across time. And if we apply some intervention, what happens is we're trying to change the mixture within the infected compartment or beaker. So maybe we have some people taking on mask wearing, or doing social distancing or something like that. Whatever we enact here, the goal is to ensure that it alters the rate of the reactions when we mix together. And we can show here very easily the impact of that. So R0, as I mentioned, is a ratio of 2 rates of reactions. If that went down by less than 1/2, for example, the epidemic curve could be significantly flattened, and most importantly, it would drop below whatever could be some carrying capacity for infected people. And because there's exponential growth, and particularly the R0 is in the exponent of that growth, small changes can often have large effects later on, and this is perhaps part of the crux of why it is important to have that public campaign to tell people to practice social distancing and so on. So if we look a bit more in detail about how you control the epidemic, so we do want to reduce R0, but how can we do that? And effectively what we're doing is limiting the rate of the central chemical reaction. And we could sort of try and use kinetic theory of, for example, gases colliding, to kind of think about why, at least conceptually, why certain measures in place might work. So, for example, if we think of temperature as an average kinetic energy of collision, then if we lower the temperature in some sense, or which would correspond to limiting the rate at which these collide, we can potentially slow the reaction down. And that's kind of what's behind limiting movement. If we do social distancing, reduce travel, we reduce sort of the influx and movement and potentially reduce this rate here, the rate of contact. As I mentioned, for K is equal to beta divided by N. So what else could we do? Well, obviously the concentration to think about, which also controls the frequency of collisions, and also explains why crowded areas, which would be quite densely populated cities, for example, you could sort of think of it as regions of more concentration. So what we want to do here is design some interventions that could minimize sort of the surface area or exposure to collisions. So remove ourselves from the homogeneous media to some sort of heterogeneous situation. And some ways we might do that is we might tell a bunch of susceptible people, as is being done in during this pandemic, to self-isolate, to sort of remove them from the general beaker. So there's sort of a sort of heterogeneous component there. And that could dilute the S. What we could also do is we try as quickly as possible to identify infectious people and then isolate them, quarantine them, put them in a hospital or whatever. Supposedly that pulls them out of continuing on. And as I mentioned before, the longer they're in the population, as long as their infectious period isn't expended yet, they can keep infecting. So that's where the gain there comes from. And that could be considered diluting I or even reducing the lifetime of the infectiousness. Something to point out is that there's a sort of parallel study of these where they more explicitly model the contact networks. And if you do that, it sort of comes down to more sort of rigorously accounting for different types of heterogeneities introduced by these interventions. So let's have a think about vaccination now. So previously, all the measures I've spoken about before, whether it be quarantine, self-isolation, social distancing, they're sort of all trying to do the same thing, reducing beta, reducing reducing gamma, shortening lifetime, reducing SOI concentrations. But they're all non-pharmaceutical responses. And while they're very important when you have novel pathogens, they're not a real long-term measure that could be in place. For example, if you wanted to stop, or as lots of debate is going on, if you want to stop second and third waves of infections, enacting things like social distancing or lockdown, you'd have to sort of reapply them ever so often. So one of the best ways to control, especially control in future, an epidemic is obviously vaccination. But vaccination does something a little bit different. What it does is, so we have to think about, again, the kinetics, and particularly let's think about the rate of production of I, the infected. So let's say that, so going back to our standard SIR equations, let's say that we could work out what the net rate of I is. I won't go into the maths, but it comes down to this inequality. And if you solve it, what you get is this, the number of susceptibles at the beginning of the epidemic divided by the total number of people needs to be greater than 1 divided by the basic reproduction number. And what vaccination tries to do is it tries to reduce this a priori coming in for, say, second waves or later infections. So that idea is that some fraction of the population will now start off in the recovered beaker. So our initial conditions will change, and S will become a limiting reagent. So if we look at that a bit more, we could say V was a number of vaccinated, the number of vaccinated people at invasion, which is when you say have a reintroduction of a pathogen. And then the number of susceptibles that we have available to be infected will be the total number minus V. Of course, these V could be thought of as already being in the recovered compartment. So if we define P as the vaccinated proportion of people, what you could show is that your new outbreak will not start or will not grow into an epidemic if the proportion is greater than or equal to 1 minus 1 divided by the basic production number. And this is what they mean by herd immunity. And by that, to clarify, it means that you want to vaccinate a sufficient proportion of the population such that you're greater than or equal to this threshold here. And we could sort of plot that and look at, for example, where COVID-19 sits on it. And what you'll find is for R0 of about 2.5, you want at least 60% of the population to be vaccinated or to have immunity to prevent future outbreaks. And this is obviously something that's being considered a lot, and it's sort of with more complex models than these, but the idea holds the same. So you want to sort of section off or remove a portion of the susceptible reagent. Now, I've spoken a lot about R0, and I've spoken a lot about how it influences control. In doing so, I've not spoken a lot about the timing, which is very important as well. So the duration of infectiousness, that does matter. And that sort of accounts for ideas like incubation periods. So for example, COVID-19 has about 5 to 6 days, could be up to 14 or more. And this gamma term can truly change the effectiveness of control measures as well. And perhaps one example of that was why pandemic flu was harder to contain than SARS. They both had similar R0 values, but one of them had a shorter time in between infections, meaning that it spread more quickly. And that was one of the reasons that was flu, and that was one of the reasons why it was a bit harder to control. So we think a little bit more about delays. So incubation periods matter a lot. There's sort of the time between when someone's infected and then actually with some visible symptoms. I can transmit that infection. So they're effectively a delay within the whole process. And we could model that again with another beaker. So what we do is we take our original infected beaker and we sort of split it into a group of infecteds and a group of people who you could kind of say questioning, but they're exposed. They've been exposed to the infection. We're not sure what's going on, but they will eventually become infected. So from the previous SIR model, we have the same reaction here, and we have the same R0 actually. But what has changed by accounting for delays or incubation is that the exposed compartment or the exposed species has now jumped into reaction. However, the rate of that reaction still depends on I. So there is, so I is sort of serving as a catalyst for the first contact process reaction. The E exposed term then eventually with 1 and alpha, sort of the latent period or incubation period, eventually does go to I, and we could kind of consider E as sort of an unstable intermediate within this reaction system. And this is sort of a stepwise reaction. And we could describe different types of delays by simply putting on different alphas and extra compartments with different E's. And that's often what's done when you want to describe different types of incubation distributions. I've spoken a lot about sort of the simplified versions of these models, the SIR and the SEIR, but it's kind of worth also thinking about some of the extensions that people place into them to sort of better describe realistic epidemics. So one of the first assumptions was well-mixed populations. In reality, mixing can actually be quite associative. So it's by some common attribute of people. And to sort of get that into the model, we would need to define a contact matrix, which shows how contact or interactions between people stratify by certain properties. And here's an example of one that was generated for a COVID-19 study. And I guess one of the key things you could look at, for example, is in the work section, as you'd expect, there's a strong age association between working people, whereas in school, there's this group of people here who are school-age children, so their contact patterns will be quite different. There's a lot of heterogeneities at play. We could also think that the rates of the reaction, the betas and the gammas, actually aren't constant. So we could have seasonal effects in contact. And one of the ways to do that is we might replace the beta in the previous reaction with some time varying fluctuating function that can describe seasonal dynamics. Another point I made was we had previously been assuming that the system is closed, so there's no entry or exit from it. In reality, with some diseases, you need to take into account what they call vital dynamics, so the births and deaths of the population, the demographic changes. And you can do that, and how it's often done is you add a bunch of extra reactions. So for example, we might have S, I, and R, or basically any person in the population dying with some rate nu, and then susceptibles being born. This phi just means like comes from nothing, so this being born with rate lambda, and you could sort of then describe fluctuations in population on top of the epidemic. So if we do some of these things, another key point I haven't spoken about is spatial heterogeneities, for example, where geography matters. It sort of links into not having well-mixed media and also not having homogeneity. So, and there's been a couple studies as well currently which are trying to look and implement some of these extensions. So for example, in this model here, what they've done is they've added on more species. So they've accounted for hospitalizations or for critical care. In this model here, what they've done is so they see SEIR, by the way. So they're using the SEIR, but what they have is a potential for travel. So they're accounting for geography. And this last model, it might be a bit hard to see, but there's these subscript i's. And what they're doing here is they have another SE sort of IR type model, but they've stratified it by age, which is where this I comes from. It describes different age classes. So these are all examples of the same chemical kinetic model actually in play with a couple bells and whistles. And as mentioned at the beginning, one of the key points of using these models is to try and predict what's going to happen in the future. And this was one study where they looked at, so they used the SEIR model. They had an extra component called S, which means that some recovered people will return to being susceptible. And they used such a model to sort of predict what would happen if you implemented lockdowns sort of across time. So that's what these periods are. And you can see that models are providing a sort of very quantitative idea of what's going on. So under certain conditions, you could look at how the epidemic might peak and fall, while keeping in mind how the number of total immune people, who are those that supposedly have been infected, rise. And this line here, this is the herd immunity threshold. I think they used a slightly smaller R0 than I've been using, so hence why the number is a bit below 60%. But effectively, they're modeling different changes that could allow us to hit that herd immunity change. So this is all examples of these models which start off from a very simple chemical kinetic basis being actually you inform and understand policy. I'm going to move away a little bit for the second half of this talk to another type of model, and that's what's called the branching process model. So the reason we're changing model now is that this allows us to make different types of predictions more easily, and it's sort of considered the second most popular approach. Now, in this model, we have new infections, small I. So it's no longer the total number of infected, but the new infections are sort of its derivative, propagating as a chain reaction. And a chain reaction could be, for example, like a polymerization reaction. And what we might have is, so for example, for COVID, I don't know, it jumped across from a bat to maybe a pangolin, it's not clear, but we have that first infected person then seeding an infection. It's sort of propagating across generation times. In this example, I put R0 at 2, where R0, going back to its definition as the average number of secondary infections per primary infection, will directly lead to this sort of binary tree. We could add some stochasticity into it by saying that the number of new infections at any generation actually has an offspring distribution around R0. And what that means is that the actual number of links here will vary with time, but on average will be R0. So we can look at that in a bit more detail. So an offspring distribution is quite a neat idea, and it sort of also comes out of demography, where you think about where you think of the infection as sort of a reproductive process. And with chain reactions, of course, they're autocatalytic with positive feedback. Now, with the offspring distribution in this sort of deterministic example initially, what we'd be assuming is that everyone infects R naught people going forward. We could relax that homogeneous assumption and say every individual can in fact infect mu people, where mu is drawn from some gamma distribution with a parameter k and a mean with two parameters k and r naught divided by k. But the key point of this parameterization is that the mean value of mu will still be r naught. And we could look at various viewpoints of this gamma distribution. So for example, if k is very large, tending towards infinity, you'll get deterministically on the r naught value, which is its mean. And as you decrease k, it sort of starts to spread out and even gets this sort of exponential type looking form, or even hyper exponential type looking form. So why is this important? Why is it even important to understand this sort of offspring distribution? Well, because that allows us to model super spreading. So super spreading is something that was talked about a lot at the beginning of the COVID-19 pandemic, and the idea that certain individuals can infect a lot more than the R naught value. And putting down this sort of offspring distribution and seeing what it leads to is probably the key way to describe super spreading and to understand what it's doing. So if you look again, so going back to these distributions with their various k values, so for the abusive notation, this k in no way relates to the reaction rate we were talking about in the first half of the talk. So if you look at these distributions, what you've noticed is as k decreases, they sort of tend to start being pushed up towards the 0. But what it also means is down on the tails, you're going to have some different behavior. And if we plot the probability of mu, so the individuals, the number of people that an individual will infect, drawn from that distribution, if we plot the probability of mu being greater than R naught, we'll see that for the small k values at, for example, 20, which is 10 times R naught, we have larger probabilities. So what that means is we have a higher probability of more than R naught offspring, and that is what defines super spreading. The super spreading emerges from thinking about things like chain reactions, or can be modeled at least. It can also be modeled within compartmental models, but it's a bit different and involves changing rate constants. And this super spreading term is important because COVID-19 actually has this k parameter of about 0.1, or at least some recent estimates suggest so. But interestingly, a lot of other infections, a lot of other diseases have been looked at from this perspective, and they often also have small k values, as you can see here. SARS as well, as you can see, is between SARS is on the side where you can have super spreading events. And a super spreading event, so for example, with SARS occurred when, or can occur when, say, someone is in an elevator and then, I don't know, coughs, and then it's transmitted to everyone in that elevator almost at the same time. That's an example of a super spreading event. And the way to sort of get it down into the maths is to use these offspring distributions. So another sort of key takeaway, as all of the models I've spoken about before, is then what does this tell us about testing and particularly about control? So an interesting point with what we call heterogeneity in this case, which is having smaller k, is that in the offspring distributions, there was an increase in the probability of infecting no people. And that's very important. So what happens is, in an epidemic, now we have this sort of mixed order reaction. You could have, say, some people who might adopt some measures population-wide, which is social distancing or wearing protective equipment, and that will reduce the average R naught, which is very good. And that's sort of the approach we were taking in the first half of the talk. However, you could do a bit more. You could identify super spreading links, so things such as contact tracing, and hopefully pull them out before they can continue along in their infectious period. So you're removing hubs from the network of reactions, and that's been shown to actually be more effective than just population-wide measures. And so, for example, here, if this person was going to lead, or this super spreading event was going to happen, and we were able to isolate that infectious agent early, we might save ourselves a bunch of people there. And if we do that, and with the, as I mentioned before, the increased probability of no infections being passed on by some people, we could actually cause a cascading failure and cause the epidemic to die out. So this is another way of thinking about control in terms of chain reactions and disrupting the key links of the chain. So this brings us to our second key analytic, the effective reproduction number. Now, previously I talked about the basic reproduction number, sort of, it does hold across, it is an important parameter across the epidemic, but it's strictly defined from what happens at the beginning. This is how we account for reproduction number changes across time. So we could sort of describe the effective reproduction number at time t as the R0 value multiplied by the proportion of susceptibles. And as you can see before, as this number is always less than or equal to 1, if R0 is less than 1, we also have RT less than 1. So there is a correspondence with thresholding behaviors. And this is a really useful analytic because it's good for real-time understanding of the behavior. Particularly, you could check from the RT value if an intervention is working or if a second wave is imminent. And one way to think about that is, for example, I simulated number of new infections across time here and the R of t value causing that. And if you look for regions where R of t is above 1, you do see peaks coming in. And regions where R of t is less than 1, you do get troughs. And that's sort of like the controlled region. And this updates almost in real time, so it's a very useful outbreak analytic. And once again, it has a meaning in terms of reproduction and chains, and it's the average cases per infectious case in a population, maybe with some immunity or with some interventions. And you can sort of think about that as the effective chain reaction, the effective reproduction. Well, it is effective reproduction, but sort of like it controls the effective chain reaction. And this brings us maybe to a sort of neat increase in complexity from our previous simple branching processes, such as these. So in the initial branching process I was talking about, I didn't talk too much about generation times, but they sort of influence the rate of spread of the epidemic, sort of in a very similar way to the infectious period in the first half of the talk. That is the gamma parameter, rate constant. So if we go back now, we get to a variation of branching process, which is called a renewal model. It has an origin with the work of even the great mathematician Euler. And what we're saying is that the chain reaction now has some sort of age dependence or time dependence. And we could describe this whole process. I've removed the super spreading component for this, but describe this whole process as new infections across time depending on effective reproduction number, previous infections, and some weight. Now this weight is actually a probability, and it's the probability that it takes S days for infections to go forward in time. So we multiply that by the number of people who infected S days in the past. Now this distribution, W of S, it's called the generation time distribution, and it's very important as well for epidemics. This also is like a nice way to summarize what's happening in an epidemic, because it says there's a size parameter, the sort of offspring produced, and there's a time parameter that sort of determines how past infections influence current ones. And within this equation, even though it looks sort of complicated, you will get the exponential growth behavior and some of the other similar dynamics as mentioned in the earlier part of the talk. So there is, it does keep, even though it looks quite different, it does keep a lot of the behaviors and statistics. So, and this generation time distribution, which causes the random timing of infection events, you could also think of it as similar to the random timing in stochastic biochemical reactions. So this brings us back to time delays again. So before, in the branching processes, we're talking a lot about the size in terms of number of offspring. Now we talk about the timing at which those offspring are produced. So the shape of the generation time distribution will control the growth rate of the epidemic. And that can actually be shown explicitly, in which you could look at different generation time distributions, such as these, and you can actually map them on to the relationship between effective reproduction number and growth rate, and you do actually get a notable difference. And even though this might look small in this plot, these numbers are, of course, exponents in the equation, so of number of infecteds, so they can have a significant impact. That's why learning about WFS is also very important in an epidemic. And it's probably a good point to mention that when we're using these models, they're always key things to learn about, but often they fall into a category of size and a category of time. And whereas in the compartmental models, that was R naught and gamma, here we have WS and RT. And this WS implicitly includes things like incubations and infectious periods. And you could actually map it right back onto the behaviors, at least population-wide, of some of these compartmental models we've spoken about before. If we look back at our chain analogy, what we've done is we've sort of put probabilistic weights on the timing of branching events. So while this person maybe on average might infect 2 people, the time at which those new infections come into the population will vary depending on W. For example, this W of 2 means it took 2 days for this new infection, but 1 day for this infection. So if we want to think now about just a couple more limitations and extensions of the branching process renewal model, one thing that we've assumed is that the generation time distribution is stationary, it does not change. That might be violated by control policies. As I mentioned before, in the compartmental part, you could reduce gamma by social distancing, and that would change the generation time distribution, for example. There's still an underlying assumption of well-mixedness here, or that individuals still come in contact in a certain specific way, but you can create spatial versions of this process. And probably one critical point that comes out from the second type of approach is that we do not actually usually see IFT, which is the number of new infections T. And that's because of reporting delays or bad testing. There is some way to account for that by what they call nowcasting methods, in which they have a model for how many infections might be missed, but that's still imperfect. And this really drills home the point that testing could be a real limitation to some of these models, because if the I values are all wrong or systematically biased, we could really get wrong impressions about the reproduction numbers. And you can sort of think of that explicitly in chemistry as if instead of being able to measure correctly your concentrations across time, you measured some really noisy version that had some sort of systematic bias, your rate reaction constants that you inferred could be terrible. And so it's just a little example, also with some work I've been involved with in terms of using renewal models in COVID-19. You could use them to examine how. Sorry. Yeah, I'm getting some feedback. You can use them to examine how the number of the effective reproduction number changes varies across countries, for example. So here we have a plot that used renewal model type measures to sort of get a distribution of what's been going on in different countries. You could also add a couple more bells and whistles and try to link it to deaths. And here's some work from Imperial where they sort of tried to predict the daily number of deaths using a sort of renewal type approach with some extra details. And so the key point of renewal models is that they provide a lot of evidence in real time that could potentially help assess the situation going forwards. And this brings me to sort of like the last point or two of this talk, which is, so across this talk, I've been sort of introducing a model, maybe explaining how it relates to chemistry, and then adding on a bunch of things to violate simplifying assumptions. The thing is, we can always add on these more realistic heterogeneities that you might think of, say, more compartments, age extension, so on. But that's sort of almost underlying an idea that sometimes is taken too far, which is the belief that the more there is some physical process, and the better we can approximate it, the more realistic our model is. But that's not always true. Specifically with a lot of compartments, if you don't have, you could often end up in a situation where it's really difficult to debug or validate what's going on. Some of these models could hide biases. All of these models, by implementing certain equations and so on, as mentioned before, contain testable hypotheses. Some of those hypotheses could get hidden when we add in, like, say, extend to all these variations, such as different types of infecteds or hospitals and so on. Maybe do that, you could actually end up misinforming policy. So one idea that's kind of like related to my work is to sort of think a little bit more about that. And perhaps one way going forward is information theory, which changes the definition of what a realistic model is. It's not one that better approximates necessarily the physical process, but it's one that can communicate that process within the limits of available data. And you can sort of think about it as this sort of balancing act around the data between details and reliability. And so the key point of just putting this in is just to remember, and also with all the reporting of different cases and deaths in the news and so on, it's key to remember that clever computation cannot replace better data. There are limits. And that's why good testing and surveillance will be essential in going forward, especially with COVID-19, where there's been a lot of debate about the reliability of the data coming in. And this brings me to just a summary of the work. Effectively, this whole talk has been based around the idea that there is a significant mathematical overlap between reactions and epidemics. As hopefully I've shown and provided some ideas from, there's similar equations and statistics, also identical assumptions often being used to understand both how reactions occur and how epidemics occur. Controlling an epidemic often always boils down to reducing the rate of some reactions or reducing the supply of reagents, such as the susceptibles, in a contact process or chain reaction. The impact of an epidemic is, again, often measured in terms of its equilibria of the reaction, the yield of a product that relates to, for example, attack rates, lifetimes, and doubling times. And perhaps the most important takeaway point going forward is that with all these measures, the key thing is to try and identify as correct as possible within the limits of the data, the reaction mechanism controlling the dynamics of the epidemic. And I guess also in chemical kinetics, the key is to understand how the molecules are interacting, by what mechanism they're doing so. And in epidemics, we use surveillance data for that, but it's really important because things like if reactions are reversible can have a huge impact. And by reversible, I mean, for example, if the recovered people went back to being susceptible, or the infected people just went back to being susceptible immediately, so there's no little immunity, that could really change how we try to control a reaction, and that could just get us back to the case of the little village in Sheffield, where we didn't quite get the mechanism right. So I hope that was clear, and I'm happy to take any questions.
Okay, Kris, thank you for that. So yeah, if anyone wants to ask any questions now, we'll use the text box on the other typing one rather than the sound. So yeah, feel free to ask questions.
Okay, so questions come in. Thanks for talk. The reason we can do kinetics or thermodynamics in the first place is because the populations of species and chemical systems are sufficiently large for them to follow statistics. If you want to study an epidemic in a village of 100 people, will the measurements be of any use and applicable to kinetic modeling? How big does the population have to be? So that's quite a good question, and that relates a lot to whether you're doing population-wide or say, more intensive studies. So you're quite correct that some of these SIR models might not fit, for example, in, say, really small areas or small numbers of infected people. And one of the things that sort of relates exactly to this is the smaller an epidemic is, the less we can learn about it because there's less data. So I don't know any specific threshold number for when these, say, the SIR models become a good deterministic approximation, but there are agent-based models where they try to model individuals at that level, and that is meant to sort of take a probably better account of the stochasticity involved in smaller situations. Because the key difference, as you rightly point out, and even in chemistry, is that you could go from mass action to more stochastic behaviors where you could get things like bifurcations and bimodal behaviors from there being a smaller number of molecules. So hopefully that gets that. Okay, so should we be quoting the same R value for the whole of the UK, or should we have a different one for each country or county? So that's a good question. One of the studies, due to perhaps a lack of data, was trying to, for example, pool the changes in R naught or R from different countries. I think we should be definitely looking at different countries, and then we should assess what's going on at smaller scales, because as a single parameter, it does provide some guidance, but it could go very wrong. So for example, so if you looked at smaller regions contributing to a country's total overall R, you could get things like what's called Simpson's paradox, where the behavior of individual counties could vary. So you could have some counties with rising epidemics potentially, but the overall look could be much worse because it's smoothed by maybe large areas that have smaller or even epidemics. So I think it's good to start initially, especially when you have less data, to countrywide, and then to sort of get into more detail as better data emerges. I've wondered whether R should have any uncertainty. So yes, so actually, usually when people practically do this, so for example, if I go to, actually this actually shows it directly. So these were using renewal models, and they would simulate many different types of epidemics with the same statistics, or do bootstrapping, and you would get a certain uncertainty around the R. And this is showing it here, where, for example, actually in the UK, it seems like it's mostly gone below 1, but there is this little bit of uncertainty that it could still be above 1. This is about a week's old, by the way, so I'm not sure what it looks like right now. But yes, uncertainty is very important around the reproduction numbers. Might be a naive comment, but it seems that when the model doesn't fit the data, just increase the complexity, i.e. add more parameters or add noise to the parameters. Is this overfitting the data? So it definitely can be. It definitely can be. So this was why I was talking about, and there are other measures in place. It's really important to do model selection to sort of balance reliability against complexity. And usually modelers would do certain things like sensitivity tests, or they would check, there's a bunch of criteria, like say the simplest is the Akaike emission criteria, to try and work out if there is evidence enough to extend the model. However, sometimes you could end up in a situation where there's hundreds of parameters and it is quite tough and potentially overfitting. So it is an issue, but I think it's an issue throughout statistics. And there are ways now, especially in R, they're including a lot of options to assess, well, I wouldn't say model correctness, but model suitability given the amount of data.
Okay, thank you, Kris. Yeah, that was a really interesting talk, and thanks for answering the questions. So unless there's any more, we'll leave the session now. So thanks once again, and thank you for attending, everyone.
Yeah, thanks for having me. Pleasure. Thanks. Okay. Bye. Okay, I'll be heading off now as well. Bye.
Actually,
oh, actually.
One question. So
okay.
The R0 value higher for SARS than it is for COVID-19 if COVID-19 is spread further?
So the thing is, it's a good question. So one of the things is, especially media has been pushing a lot R naught, but R naught isn't the only property leading to spread. I was talking a lot about, for example, with the case, let's see if I could find it, or with pandemic flu versus SARS, where they were harder to control and there was a different level of spread. And one of the reasons for that was the duration of infectiousness, or in terms of the renewal models, the generation time distribution. So R naught alone is not enough to really describe spread completely.